Hi, I am Ecrin from Bilkent University, Ankara. In this video, I will talk about my term project for Foundations of Magnetic Resonance Imaging class. My project is to simulate the effects of main magnetic field B0 inhomogeneity. To do so, I implemented MR imaging simulations in MATLAB. The simulation toolbox that I implemented is capable of applying RF excitation and slice selection. It can simulate the effects of T1, T2, T2 star decays. Also, spin echo sequence is implemented as a basic MR imaging sequence. Furthermore, it is possible to change several important imaging parameters such as field of view, FOV, and number of samples. And as object, I use a dataset from this source you can see here. There are two gray models, each containing the information on T1, T2, T2 star, and PD values. Starting with RF excitation, in MRI, main magnetic field B0 is always on, and it is ideal same everywhere. Then we have magnetic field due to gradient. So there is additional linearly changing magnetic field on top. And then RF pulse is designed to excite only a certain portion of the body here with thickness delta Z. Here we can see we apply a single-like RF pulse, and in Fourier domain it corresponds to a rectangular shape. And to implement such a RF pulse, I use Hamming window with given formula. Here tau is the duration of RF pulse, and A is the scaling of the pulse. Tau is related to bandwidth, which is found through delta Z, thickness of the desired selection, and slice selection gradient, G is the set. Hence, after deciding delta Z, we can find the value of tau, and to decide the value of A, we can find it through the Philip angle, and that is the integration of the RF pulse should yield the Philip angle. So to adjust the desired Philip angle, we can adjust the A. And finally, Philip angle with respect to Z is found from the Fourier relation, as you can see here. So after these explanations, here two graphs from slice selection process. First one shows the RF pulse in time domain, and the second one is the Fourier correspondence of it. Here it can be clearly seen that only 4 mm portion of the z-axis experiences a pi over 2 Philip angle. And here another result for 20 mm this time with pi degree. Fun thing to observe here is that since in Fourier domain signals expanded from the comparing to the previous one, in time domain it becomes much more narrower. And after RF excitation, a simple spin echo is implemented. Here there are two RF pulses in one repetition time, and in echo time, that is here, we record a signal with T2 decay rather than T2 star decay due to alignment of spins at time t. And in simulation toolbox, user can give several parameters as input. Those are field of view in x and y directions, number of samples in x and y directions, echo time, repetition time, slice thickness, sampling period, and slice selection gradient strength. And other parameters are calculated from the given parameters through several formulas. And now we can talk about signal equation. The infamous signal equation can be seen here. And here kx and ky are found from these two on right. And adding T2 decay on top of it, the signal equation now becomes this. Then we can add field inhomogeneity in a similar way. That is, there is an additional field with BE, and the corresponding frequency is omega E, and we can add it to the signal equation as such. Then we take the signal equation with inhomogeneity and do some rearrangements in it, which is actually we only rename time variable to t prime. And besides, in this form we see that there is actually a weighting function to the object mxy, and besides, the spatial variable x now becomes x prime, that is x minus omega e xy over gamma gx. So in the image that we will simulate it, we expect in the results that there is a shift, a displacement in the readout direction, which is x direction in this case. And before going on B0 inhomogeneity simulations, I present several different results from simulation toolbox. Here, by changing the values of TE and TR, I obtain T1, T2, and PD weighted images of the selected slice. And as expected, we can see the bright parts of the brain changes consistently. And another demonstration is about field of view. In the first image, we see that 30 cm by 30 cm is enough to avoid overlapping in spatial domain. However, as field of view reduces, overlapping starts to occur, and in the extreme version, it's not possible to realize underlying image at all. And as for inhomogeneity, in the first case, I had 0.1 millitesla deviation homogeneously, that is throughout the scanner volume. Actually, this value is normally too much. Normally, what happens is in MRI scanner is that there is 1 or 2 ppm deviation at most. But since the resolution in my simulator is not high enough, in order to see the displacement in the readout direction, I needed to increment the value of deviation, and calculating the shift amount from the formula, I expected to see approximately 0.6 millimeters shift in the readout direction. And first I checked the results with a dummy phantom, that is a phantom with a diamond shape. In this slide, it can be said that there is no shift at all, but to see it better, I visualized the results with MATLAB's image pair function. This function takes two images as input and then displays the resulting image using the differences of the two images. So here we can see that there is a shift in the left direction. And also I use the brain model again to simulate the effect. Since the additional field is homogeneous everywhere, there is only translation in the readout direction, that is x direction. And then I created another additional field. This time the additional field changes with respect to both x and y coordinates. And by applying 1 minus of it, actually I reduced the deviation in the center of the scanner. And to show a more exaggerated additional field, I can just directly take this one, and this time the additional field on the center becomes much higher, so I expect to see much more deviation in the center. And the results due to this additional field can be seen here. This time, since everybody experienced a different amount of displacement, we see that image is actually completely destroyed. But since the additional field is symmetric, actually the effect is also kind of symmetric. And also, since the value of the additional field is high, also we see that there is also signal loss due to this effect. To conclude, in this work, a simulation toolbox in MATLAB is implemented, which is capable of simulating MR imaging sequences, and also it can demonstrate the artifacts due to B0 inhomogeneity. In this work, the effect of B0 inhomogeneity is not taken into account with slice selection. Normally, I should have included that as well, since I take the deviations from the ideal field quite large, in order to show off the displacement better. I hope you enjoy my work. Thank you for listening. To conclude, in this work, a simulation toolbox in MATLAB is implemented, which is capable of simulating MR imaging sequences, and also it can demonstrate the artifacts due to B0 inhomogeneity. In this work, the effect of B0 inhomogeneity is not taken into account with slice selection. Normally, I should have included that as well, since I take the deviations quite large in order to show the displacement. I hope you enjoyed the work. Thank you for listening.